Just let me know if you can't hear me or if you can't see the slides. Yeah, I've been at Tri-Cities for quite a long time. And I teach machine learning as part of my workload there. And Kathy came to me saying she wanted to do a master's thesis in cybersecurity. I told her right off that I didn't really know much about cybersecurity, wasn't my expertise, but I would try to find a project for her. And I contacted a fellow professor, Luis De La Torre, which I think will be here this afternoon. And he has contacts at P&L, and we found a project for Kiate for her master's thesis, which had a lot of machine learning in it. So that means I enjoyed it. And basically it was to cluster code vulnerabilities and try to understand attacks by how we cluster code vulnerabilities that open up software to hackers. So I'm going to give a presentation about our methods of clustering code vulnerabilities, and then I'm going to turn it over to Kathy and Tim and Luis, and they're going to actually give you some hands-on with the data itself. My hands-ons, which are near the end of this theoretical presentation, will be on a very simple and data set, which is commonly used in teaching self-organizing maps. It's a clustering of iris flowers. So with that introduction to myself and what I know, let's get started. This first slide here is basically introduces you to self-organizing maps. And maps have this very long history of human use to accomplish data compression. We can look at a map of the United States and we can visualize immediately where all the states are at and even show the capital of the state. So we can throw a lot of information onto a map, and that's the way humans generally like to do data compression. And self-organizing maps accomplish the same result by finding, taking the vectors that make up a data set and finding prototypical vectors. And these prototypes are a smaller number of vectors than actually in the data set, but they're designed to essentially contain the content of the whole data set in just a few prototypical vectors. And this is called a self-organizing map because we have an algorithm that if you feed the algorithm a data set of clusters of a specified length and you name some attributes of the map you want, it will find the prototypes. And so we're going to first of all discuss that algorithm, and then we'll do some hands-on exercises in implementation of that algorithm for the iris data set. Let me see if I can make these slide changes. Okay. When I'm teaching SOMs, I really love to show this slide. It's a way of picturing the effect of clustering by SOM. Here we have this first bar, which is just a bunch of colored pixels, lots of them. That represents our very large data set. And each of these pixels is characterized by a vector with three components, which is the proportion of red, green, and blue in the color of that particular pixel. I don't know how many pixels there are there, but there should be several thousand pixels in that first bar. Now and then we pass that set of vectors to the algorithm, and it looks for prototypes. And those prototypes are also three component vectors with the proportion of red, green, and blue of a prototype. And we would, if we showed those prototype, there would be the combination of red, green, and blue that gives us purple or yellow or brown or chartreuse or whatever. And those would be the colors that we think we can use to explain all of the colors that are in this very large data set of colored pixels. And in order to illustrate the clustering based on those prototypes, we'll find the prototype that's closest to each of the color of a pixel, and we'll group all those pixels that are close to a given prototype in one region, and that'll produce these color bands. And these color bands give us a map of what colors are present in these pixels. So here we have various bands, color bands, and they represent different levels of refinement of the prototypes. The process of finding prototypes is an iterative process, and so as we train more and more on the vectors in our data set, we get better and better prototypes of the colors, and eventually we get this set of color bands on the bottom row of this illustration, where we can begin to see, most of the colors that are in these pixels: reds, browns, light greens, blues, and purples. So here we have fairly well-defined prototypes of the colors of these pixels. And if we arrange the pixels by what prototype they're closest to, we get meaningful color bands. Okay. Well, this famous machine learning professor, Conan, published in 1982 an algorithm to find prototypes. And it's an algorithm that's basically a deep learning algorithm. It takes the input vectors, here are these nodes here for our red, green, blue color vectors. The red index, the green index, and the blue index, those are the input values. And that input is connected to all 16 of these output arrays. So this is a neural network, if you wish to call it that. But the peculiar thing about this neural network is that the output is an array, and the input vector is connected equally to all members of the output array. But the training is basically the same as any neural network, initialize some weights, test to see what you get, do some back propagation against a standard and change the weights again. And so just go back and forth weights until you actually then converge on an output. And we're going to talk about that algorithm in a little more detail here. But again, to illustrate what's happening here, machine learning people like to think of the input data as a data space. If the things we're interested in have only two attributes, two features, height and width, for example, then we can actually think about the data space as a planar object, and any point in that represents a possible member of our data set. So this is a way of abstracting the concept of a input data set. And here is some bunch of dots that are in an array, sometimes called a lattice, and they represent the output nodes of our SOM algorithm. Those are the things that are connected to the vectors here in this data space. And if we think of a given instance in the data set, which we call X, if there are lots of instances there that are like X, then there will be a node here in our output array called I of X, which will be the best matching unit of the instances in the data set that are like the vector X. So, they're going to be, vectors that are, close in the Euclidean sense to this vector X. And they're going to map that particular characteristic of the input data onto this node I of X. So that's the first thing that the algorithm has to do, is it has to identify these particular nodes that are related to particular types of data in here. Now then, the weight, W sub I, that connects input nodes of the type X to this particular node in the lattice, that will become a vector that we call the prototype of instances of type X. So again, going back to the previous slide, basically we're going to find pixels of similar colors, and they're going to be associated with a particular output node here. Maybe the green pixels are associated with this node, and then the weight vector that connects those green pixels to that node after convergence is the prototypical vector that we're looking for to give a reduced representation of the problem. Well, Cahonen was obviously a very talented machine learning person, and he devised this algorithm, which has basically three steps to it. The first step is involves a definition of a discriminant that we can use in competitive learning. That is to say, there should be a discriminant which, if I present the network with a particular input vector, that discriminant will be largest at one particular node. It'll be a defined value on all the nodes, but it'll have some largest value on one particular node, and that we'll call that node the winner of this competition. And that's the first step in Cahonen's algorithm. Well, then the winner, being a good administrator, gathers a team of nodes around him, and that team is going to help him, have a very strong response to the discriminant, so that even though he was the winner by himself, when he gets his team together of nodes that are close to him, he'll even be a bigger winner, and so there'll be no questions anymore about who's going to win the competition with the largest value discriminant. And once he's got his team assembled, basically he starts modifying the weights in the connection of the input data to the output array, and he follows this rule that he identifies the weight labeled K that is closest to the input vector X in the Euclidean sense. Just take the difference of two vectors, and take the square root of the sum of the squares. And that is basically what defines winning the competition for being the node that's closest to the input vector X. Well, it turns out that computer scientists, basically want to avoid as much computation as possible. And since the output, the weight vectors are normalized, smallest Euclidean distance is the same as the largest dot product, and dot product's easier to calculate. And so the actual discriminant is the dot product of the input vector with all of the weight vectors there. And that's how we decide who wins the competition. Well, the neighborhood around the winter actually changes with iteration according to this Gaussian formula. That is to say, the basic size of the neighborhood in terms of distance on the array is given by this e to the minus the square of the distance between element k and I divided by 2 sigma squared, which is the parameter of this Gaussian distribution. And that parameter varies with iteration. It starts out to be a large variance, which means that there's a possibility of quite a few neighbors contributing to being the winner. And then as we iterate, that neighborhood shrinks smaller and smaller. And again, as we assemble our team to give us the great advantage of winning the competition of what node is closest to a given input vector. So once we've got our size of the neighborhood, that's given by this factor h sub ki of x as a function of what iteration we're on, and we decide on a learning rate for the typical cycling back and forth between the value of the nodes and what we want them to be, and then that is then multiplies the actual distance between input value x and weight vector k, and that determines how much we're going to modify weight vector k in order to use the next version of weight vector k, which we expect to be even more like the input vector x than the previous iteration. So this modification of the weights in the network basically is focused on our team for the winning the competition, and basically keeps modifying the weights to make them closer to the input vector. And as you can see here, the learning rate also decreases as we proceed in the competition. So going back to my favorite representation of SOM clustering, again, up here at the first iteration on determining prototypes, the size of the neighborhood just about the same size as the lattice. So if the lattice contains 100 nodes, then we're talking about basically having 100 nodes that are potentially cooperative. And at that level, there's not really very much distinction in the color bands. There's clearly some green here and probably some blue and probably some red. But we have to proceed further into the iteration, always reducing the size of the neighborhood and refining always the prototypes of the colors that we're interested in. And by the time we get down here to the last refined prototypes, now the neighborhood is probably just the nearest neighbors to the nodes in the thing. So we have, now we have our nice, well-defined prototypes. We go to each pixel up here. We ask what's the best matching unit, and that way we'll collect together things that are similar to our prototypes, put them in bands, and we have our map of the colors in our data set. So that's basically how it works. I'm not going to go any deeper into the algorithm, but Cahonen, of course, had a example that he loved to show to illustrate his fantastic algorithm. And so here's the famous Cahonen data set, which is basically animals, doves, hens, ducks, geese, etc. Now all the way down to horses, zebras, and cows. And here's some attributes of those animals. What size are they? How many legs do they have? Do they have hooves or feet or feathers? And what do they like to do? Hunt, fly, run, or swim? And then the each of the animals is associated with a binomial vector that identifies which of these attributes applies to the particular animal in question. Doves are small, they have 2 legs, they have feathers, and they like to fly. So that is Cohen's understanding of a dove. Okay. Now there are 60 animals here in this list, and each animal has 13 attributes, possibly chooses his description out of possibly 13 attributes. And then Cohen did an SOM on a 10 by 10 lattice. So that's 100 nodes. And so he's actually not producing any data compression. In fact, he has more nodes in his lattice than he has examples in his training set, which of course in the modern world we would never bother ourselves with such a trivial problem. We're always interested in cases where the size of the data set is just at least 10 to 100 times larger than the number of nodes. But Cohen accomplished his purpose of illustrating his algorithm on this particular example. And so here's what he got. And here's his array of 10 by 10 output nodes. And he's just identifying the node that corresponds to the best matching unit of each of these animals. Okay, so each of these animals, after we trained our prototypes, will be closest to one of the prototypes in this 10 by 10 array, and that we call the best matching unit. And we're going to go ahead and put the name of the animal in the array element that is its best matching unit. And so here we go: dogs, wolves, tigers, foxes, etc. All right. Now then, the miracle, of course, of Cohen's algorithm is that it topologically orders the best matching units, or topologically orders the prototypes. That is to say, even though the data didn't identify which of these were predators or prey, which were mammals, which were birds, all it has is a name of the animal associated with each input data. Our prior knowledge of these animals lets us associate the topological arrangement with something that's meaningful to us. So sure enough, wolves and tigers, known to be predators. Dogs used to be predators. I guess if we turn them loose long enough, they become predators again. And foxes are also predators. So we have these 4 mammals here, topologically ordered in the upper left corner of this output array, that we say, oh, these are the predators. Over here we have some cows and zebras, and they're the prey animals, mammal prey animals. And so above the middle layer, we have mammals. Below the middle layer, we have birds, and our birds are also characterized by prey and predator groups. The eagle and the owl and the hawk, basically the predator birds, and the hen, the duck, and the goose, those are prey birds. Okay, so what Cohen's algorithm has actually accomplished for us is that it topologically arranged the prototypes, which tweaked our brain for what we remember about animals into clusters of these prototypes. So if we go out there and find another predator, I don't know what that might be. Let's say a badger. We find a badger. Okay, we assign some attributes to badgers, and lo and behold, we find the best matching unit for badgers, and sure enough, it should fall up here in the upper left-hand corner of this particular output array. So we got the topological arrangement as a consequence of map production. Okay. Well, Cahonin, he thought up a whole bunch of ways to illustrate his result. And then ever since 1982, people have been, working on other ways to illustrate self-organizing maps. But here was one that Cahonin came up with. He said, well, let me design some probes. I'm going to design some probes for what I've trained here. And with the probe, I'll measure the dot product or the discriminant of each node in the output array. And I'll label that output array with the name of the vector that has the largest response, the winner of the competition for the largest dot product. And so here we have now dog is the winner of the competition for the array 1010, upper left array. And so Cahonin puts dog there, and dog also won for this one. Then wolves and tigers came on later. And so this kind of response, or called semantic map, giving test probes and seeing how various things, the strength of the response of each output nodes. Again, this fills in the 4 clusters that we recognize as predator animals, prey animals, both of which are mammals, domestic birds, obviously live in West Richland. They're also prey animals, and the predator birds, hawk, eagle, and owl. So this is just another way of illustrating the map to let us input our prior knowledge and understand the clustering of these nodes in this output array. Well, in modern times, if you call 2022 modern relative to 1982, we prefer to have a more universal way of describing the output array, and that's called the unified distance matrix, also called UMAT or a U matrix or just UMAT. And it's a function that we come up with to define the similarity between neighbors in the output array, right? How similar is this neighbor to the given one I'm focused my attention on? How similar is this hen to this dog? In terms of a prototype, is this hen prototype really different from this dog prototype up here? If so, let me define that distance. So the various nodes in that lattice have different numbers of neighbors depending on whether they're at the corner of the array or on the edge of the array or in the middle of the array. And so for a square lattice, which we've been talking about here, that's 2, 3, and 4 neighbors, depending on if you're in a corner, on the edge, or an internal array. We're going to do a hands-on in a minute for a hexagonal array, which is the most common one we use now. And it will have slightly different numbers per number of neighbors. Then we're going to calculate the Euclidean distance between any given prototype and its neighbors, 2, 3, or 4. And we're going to average that Euclidean distance between prototypes of neighbors. And we're going to display that result as a heat map with the bright colors representing neighbors that are very similar, and the dark colors illustrating neighbors that are dissimilar. And so with that approach, we can sort of universally demonstrate what prototypes clusters of prototypes that are similar, and how and boundaries that separate them from prototypes that are different. And here we've done it for Cahonin's famous example. Again, we have down here in the lower left-hand corner, we have output nodes for owl and hawk that are so similar that they're almost as similar as you can get, essentially white in the heat map. The weird thing about this is that in this way of looking at it, these eagle over here is not, even though we think of it as a predatory bird, from the attributes of eagles, owls, and hawks that we've been dealing with, the eagle is really, you know, not so very similar to a owl or hawk, and I won't try to weigh in on whether that's right or not, but nevertheless, for the attributes we were showing, we have this very high similarity between hawks and owls, and not so similar to eagles. And then up here in the upper left, we have our domestic birds, you know, similarity between geese and high similarity between goose and ducks. That makes some sense. They both like water. Doves and hens, not so similar. Over here in the mammals, again, we have our predatory mammals up here: cats, lions, tigers, and wolves, dogs. And down here in the middle, we have horses, which are obviously a prey animal, but sort of belong to their own thing. That is to say, from our attributes, they're significantly different from cows, of which I will attest. Yes, horses and cows are different, and you can have your preference, whichever you like. So anyway, this is then we have this, you know, high-level organization between birds and mammals, and then we have this fine structure that is defined by the UMAT, which sort of, you know, gives internal boundaries to our big picture of birds versus mammals, and defines our predatory versions versus our prey versions. So this is sort of the modern way of illustrating the output array in SOM. Okay, time to loosen up those fingers and get ready to do some typing into MATLAB and see if we can do SOM on our own, okay? So as I promised, this is the SOM for the IRIS data set. And the nice thing about the IRIS data set is that it is available in MATLAB by simply a load command. So MATLAB, you know, has a video that shows how to, its software, shows off its software for SOM. And in that video, it refers to this IRIS data set. And now this is a way to, you know, get a simple little code that will do SOM.
Can I interject real quick? Is everybody able to get on the AWS website to access the I think we're going to be working on MATLAB, yeah, okay. Everyone know anyone else have problems? There was some issues. Okay, we've got our computer tech here just in case. Okay, John, go ahead.
Okay, thanks, Bernie. Got to get everybody up to speed here. The IRIS data set has these characteristics. It has 3 classes of irises. Each class contains 50 records, and each record has 4 attributes. So we did a little bit better than Cahonin here. We've got a pretty substantial data set. Amount of total records, 150 records. Each has 4 attributes. And so we're going to explore that with SOM on an output array that has that's 6 by 6. That is to say, there are 36 nodes in this output array. We'll produce 36 prototypical vectors, and we're going to use those to cluster these 150 records of irises, each with 4 attributes. So the basic call to get MATLAB to do SOM is to call up this built-in self-organizing map and tell it the dimensions of the output that you want. In this case, 6 by 6. Once you've done that, then you can call this training algorithm, MATLAB, and pass your inputs to it and pass the characteristics that you've given for net. And it will return two outputs, net and TR. They will, outputs will show up in the workspace of MATLAB. And then we can pass the inputs to the net output here, and it will generate various ways to display the output array, the SOM output array for this particular problem. And here are some output options that you're gonna, some of which you're gonna call up and get the picture of what's happened. Okay. Now, I recognize that, you know, not everybody loves MATLAB. Most people love Python better, but this is a MATLAB exercise. So I put up here the, you know, sort of the navigation view of the home, you know, MATLAB, where you go and when you sign into MATLAB. And I have this little icon here called New Script. And if you click on that, you will open up the editor, and the editor will have, you know, defined some space in MATLAB. It's labeled, it's called unlabeled. It's going to be called that until you actually name it, if you want to save it. And it just gives you a place to type. And I am such a poor typist that I never type in the command window. Good grief. It takes me long enough to type in the editor. If I try to type in the command window, it would be hopeless. So I always make my scripts in the editor, and I'm advising you to open up a script and type these 7 lines of code into the editor, okay? Has everybody been able to reach the editor with the script option? Everybody's there? All right, fantastic. Let's type. Okay, so here's our 7 lines of code. Now, I did this problem this morning, and it only took me twice to get the typo errors out of it. And the reason I like to use the editor is I can copy and paste my typing into the command window, and the command window is real quick to tell me how I goofed up, and I can go back to the editor and make those corrections. So after a couple of tries, I did get this script written, and then I ran it by simply just hit return. Once it's copied in the command window, just hit return, and MATLAB will run the script. I'd say it probably takes 10 to 15 seconds for MATLAB to work on the SOM for the IRS data set. And then I'm ready to click on the output options. And the output options, in other words, MATLAB comes up with a result that lists the output options, and you can click on them. As I said before, these are the output options here in green, and if you click on individuals, you'll get different ways to display the results. And the first way I like to display the results is what MATLAB calls node connections. And the nice thing about this representation is that it distinguishes the nodes from the connections between the nodes. The nodes are these dark hexagons, and the parallelograms that are between the nodes and with these lines in them, they illustrate how this node is connected to its neighbors. As I said, corner nodes have either 3 direct connections to neighbors, 1, 2, 3 for this node that's in the upper left, or they might have just 2 connections to the neighbors here, 1, 2 for this node that's in the upper right. And then we have our edge nodes. Most of those have, some of those have only 3 connections to neighbors. They're illustrated by these red lines connecting to direct connections to its neighbors. And some of them have 5. connections. And of course, each internal node has 6 connections to neighbors, direct connections to neighbors. And because this is a hexagonal output grid. Okay. Now, the reason I like this is because the UMAT is really a function that's defined on connections, not nodes. So that when we have the heat map to show the distances between nodes, we're actually coloring the connections, not the nodes. And so that's just clarifies the fact that the UMAT is defined really on the connections between nodes. Is the connection between similar nodes or the connection between dissimilar nodes? And so that then gives us our understanding of similar prototypes and dissimilar prototypes. So I hope everybody has been able to run the little script. Everybody's got a result. Everybody's plot node connections. Okay. I hope you've been able to follow along with me in this little MATLAB exercise. I'm going to go to the next one that I like, and that's the hits. So in our data set that has 150 records in it, basically each record I find the best matching unit, and then the hits display describes, plots, illustrates the number of members of my data set that had a given node as its best matching unit. Okay. So down here in the lower left, we have a big hitter. 13 of our 150 examples decided that this particular node was the most was its best matching unit, and then there's 3 more heavy hitters right in this neighborhood of this one down here with the most hits. Well, here's another 13 up here. Here's an 11, and then there's this sort of no man's land here that either contains nodes with no hits or nodes with just a few hits. And so that's, in terms of the hit output, this is sort of a clear boundary in the output array that's distinguishing prototypes of irises here in the lower left from all the other prototypes of irises. Okay. So it looks like to me that this SOM is saying, you know, even though I got 2 classes, I got 3 classes of irises in this data set, it's saying, well, you know, 2 of those classes are just about the same. I mean, it's suggesting that we put 2 classes in one cluster and put the other class here in the third cluster. And there may be some little bit of mixing between the 2 over here and 1 over here, but basically one class should belong to associated with prototypes over here in the lower left, and then the other 2 classes should associate with various prototypes over here in the remainder of the output array. And I guess we have a big heavy hitter here with 10 hits right here. And otherwise, they're pretty well distributed. So that's how the determine, you know, boundaries in the output array based on hits, based on the number of instances in the data that choose a given prototype for its best matching unit. And here's our famous U matrix, our colorful output, one I enjoy the most. And again, it's the connections that are colored by the heat map. And these bright yellows show connections between nodes that are very similar prototypes. And down here in the lower left, we see that there are a bunch of connections that are nice and bright and suggesting that, yeah, this is probably prototypes that will allow us to cluster irises of a similar type. And then there's this nice boundary of darker colored connections that goes here from, say, upper left down to lower left also, sort of fencing off this collection of similar prototypes here in the lower left. And then there's the remainder, which has some structure in it, obviously, right? I mean, we've got a big bunch of similar prototypes up here in the upper right. And then we have, well, the suggestion of a boundary between them and these guys up here in the upper left. But nevertheless, the general conclusion is that we've got two types of prototypes, two basically ways to put our data into two clusters, one associated with the lower left prototypes and the other associated with all of the other prototypes. Well, I hope you guys were able to get these three outputs. They're kind of interesting and colorful. And you can see here where I compare them side by side. HITS and UMAT really say basically the same thing about the output array. Basically two types of prototype, two sets of prototypes, which will enable clustering of irises. Although they belong to three sets of irises, they will actually end up as two clusters of the data. All right. Well, I don't know if everyone here is familiar with k-means clustering. Obviously, k-means, if you're in the machine learning business at all, you've learned that k-means is the easiest way to cluster data. You just tell the algorithm, hey, I want two clusters of these data. I want you to go out and find centroids that are the best way to make two clusters out of these data. So you specify the k and just hand that k off to the algorithm, and it runs off and it clusters the data in two clusters and will return the centroids of those two clusters. So obviously, you know, this is the way everybody gets involved in clustering using k-means. And the thing I want to point out as I end this lecture is did SOM clustering and k-means clustering, did it tell us the same thing? Well, the biggest problem with k-means clustering is that what's the right value of k? And believe you me, you can search the literature of how to find the right value of k, you know, enough to write a thesis about it. So there's been tons and tons of stuff published about what's the right value of k to cluster by k-means. And one of those ways to decide what k is this Davies-Bouldin index. And that index basically says, I want to cluster this data by number of clusters so that the resulting clusters are the least similar. That is, I want to get the most dissimilar clusters out of this exercise. So tell me what k will give me the least similarity between the clusters that I generate my k-means. And that's called the DBI, or Davies-Bouldin index. And that's also provided by MATLAB. And I'm inviting you to have one more hands-on exercise before I turn you over to Kiati and Tim. If you like, we can use these three lines of code to see what the advice of experts is due to k-means. The first thing we got to do is we got to put the inputs, iris inputs, into a vector called x, and we have to transpose that vector. If it's a row vector, it's got to become a column vector. If it's a column vector, it's got to become a row vector. And that transition is given by this prime that follows the name of the vector. So the first thing we do is we transpose the inputs and we shove them into this vector x. Then we shove x into this MATLAB built-in that will explore numbers of clusters between 1 and 6 clusters, and will report a BDI index for that value of k. Then this will plot the BDI as a function of value of k. And again, this is another reason why I love to use the editors, because I'm never happy with the script that I produced. I've got to do a little bit more with it before I give it up. And so if I want to do this in addition to what I've done already, I just add these 3 lines to my script. Then I could just copy those 3 lines, go to the command window, find the prompt in the command window, and just paste these 3 lines to what's already been done in the command window. So that means, hey, go out to the workspace, get what you need to do, this extra job I'm telling you to do, and give me the results. So if you want to try k-means clustering and BDI index, just add these 3 lines to your script and hit another return, and you will produce this particular graph. So on the y-axis, we have the DBI index, how similar are the clusters that result from different numbers of k, and lo and behold, the DBI index is also telling us that 2 clusters is the way to organize our data on iris types into clusters that are most dissimilar. 2 clusters is better than 3 clusters with respect to dissimilarity, lack of similarity between clusters. Even though if there are 3 classes of irises in our data set, DBI and SOM are telling us that, well, better to cluster them in 2 clusters, put 2 of the classes into 1 cluster and separate the class. So this is nice validation of our SOM results. And I'm going to shut up here and turn it over to something useful, which Kiati is going to tell you about. Thanks for your attention. And if you have any questions, yell right now or send me an email, and I'll be happy to share my knowledge of this subject with you. Okay? Kathy, I'm going to sign off here.
Professor, thank you.